Hello, I thank the organizer for giving me the opportunity to present my work. The work I will present to you explores the prospect of augmented laboratory diagnosis using artificial intelligence. In terms of conflict of interest, I am statistician and data manager at Emosis. The example I have chosen is that of the functional testing of HIT by flow cytometry, the interest of which is twofold. On the one hand, diagnosing remains complicated in practice because only a few laboratories are able to use the reference tests such as SRA or HEPA. On the other hand, these assays, which are bulk assays, provide measurements restricted to mean values of platelet aggregation. In comparison, flow cytometry is very rich in terms of data. Where would then artificial intelligence play a role? Diagnosing is classifying, that is to say predicting class. For a patient, predicting if he's diseased or not, which is a quintessential AI application. To introduce AI more concretely, I will focus on the setting of HIT, where it matters to show platelet activation. I am referring here to the FCA test, whose performance was recently reported by Dr. Tardy in Biomedicines and from which Emosis has developed a commercial version. Like all diagnostic tests, it was developed in the manner shown schematically on the left side of the screen, from samples of patients whose diagnosis was confirmed. A statistical model is built and a diagnostic criterion is constructed. For FCA, the variables used are the percentages of platelet activation measured in 4 tubes, one containing heparin in therapeutic dosage H03, one with excess heparin H100, and 2 control tubes, NEG, which contains no platelet activator, and POS, containing the powerful platelet activator TRAP. The classifying rule is based on the variable HEPLA, derived from the 4 features. The algorithmic approach is much the same, only the modeling is no longer done by hand, with the involvement of a human being, but with machine learning techniques. On one side, the source of HEPLA computing is 4 values, and on the other, the source for the machine learning model is about 15,000 observation vectors of length 4 to 20, measurements of size, fluorescence, etc. For a patient, these vectors are put in relation algorithmically with the known state of the patient, HIT positive or HIT negative. Several families of algorithms are explored. We first built 10 base models, all optimized for the prediction of HIT. I will not detail these models here, but they all have demonstrated success in many classification problems in the medical field, but also in various machine learning competitions. Then the predictions of each model are grouped together by the so-called stacking process in order to overcome the weaknesses of each on certain observation and thus improve the predictive performance. All models are optimized for prediction. In effect, these models have hyperparameters influencing, among other things, which features are to be taken into account and their importance in predicting HIT. For each model, we determine the set of hyperparameters giving the best predictive performance, which is called model tuning by cross-validation. The programming is done with R's package caret, a language you may be familiar with. Cross-validation also assesses the predictive capabilities of models on new data while using all available data. This is a key point, as it prevents the model from overfitting and allows us to detect potential biases. This is how you end up involving artificial intelligence in HIT functional testing. How then can we go from involving to using AI? To this end, we propose an interface of which we build a prototype with our package Shiny with the critical criteria of easiness of use in mind. At this point, it looks like what's on the screen. The application opens in a web browser. Browse buttons are used to indicate the location of the input data files that will be used by the AI. As soon as the files are uploaded, the model will launch and will provide the results on the screen within seconds. Note the simplicity with which the input data is provided to the AI. Note also that the outputs produced are fully customizable. Other graphics, table, text, and more or less anything that seems relevant in the diagnostic aid can be implemented. Here, I took the example of patient 4023 from Dr. Tardy's study. One can read among the output results that the diagnosis proposed by the AI is positive. HEPLA method of the FCA test is also implemented and gives a concordant result. Interestingly enough, there was no clear overall gain in terms of classifying performance. The sensitivities and specificities are high in both cases. How then can AI be useful? On the one hand, it may suggest that AI could be useful in validating the relevance of the current handmade classification criteria. On the second hand, AI could also help in addressing discrepancies. As a case in point, patient 4023. He is positive for ELISA and for both FCA and AI, while negative for SRA. The presence of strongly activated platelets in tube HO3, see density in yellow in the third graph, question SRA's negative results. The visualization displayed here are well known to users of the FCA test and are intended to inform the user about the AI's prediction, to allow him to come to a judgment on the test results. To conclude and review future prospects, we have built a sensitive and specific diagnostic tool, which is also fast, operator independent, and standardizable. The interface makes it easy to use by removing operational complexity, as it directly exploits raw data and automates data processing. AI thus provides a gain in information for the clinician in order to interpret test results. While this AI would benefit from being trained over a greater amount of data and data from a greater number of different laboratories, our tool therefore provides a framework for future industrial software or mobile application, as well as a basis for continuous retraining of a predictive model in the HIT testing. Before closing this presentation, I would like to thank Frédéric Allemand and Jean Amiral, who enriched this work with their suggestions and wise advice, and my colleagues Justine Catella and Marion Grolier for their contribution to this presentation. I am at your disposal for any question.